All right, sine, cosine, and tangent are the three basic trigonometric functions, and these are some things that I always was able to apply them and figure out how to use them on math tests, starting in 8th grade or whenever I was first introduced to them. But I don't think it really clicked with me what I was actually doing with them, sadly, until I think freshman year of university, which is a long time to be using these things without fully understanding them and the differences between them and what they actually are. And I think that's because I thought that they were something much more complex than they actually were. And what I hope to do here is kind of demystify and explain exactly in very clear language just how simple these three functions, even though they're described as trigonometric functions, which is a big word, right? They're really just a very simple thing. So to start, I would like to break down what these functions, sine, cosine, and tangent, are not. And in describing what they are not, I'll draw a little right triangle here, because something that I thought they might have actually been is something physically measurable on a triangle, right? When we dealt with trigonometry and sine, cosine, and tangent, these things, we were always dealing with right triangles, right? And I think because of that, I thought, and because of the association with geometry, and geometry is a very visual kind of branch of mathematics. You can draw shapes and all of this. I thought that there must have been some kind of physical interpretation to these functions, sine, cosine, and tangent. But I'd like to demonstrate things that are very unique, very different from these three. So when you look at a physical drawing of a right triangle, even if the drawing is pretty low quality, such as this one is, you can define some things about it, right? For one, we know that if it's a right triangle, that this angle here is 90 degrees or pi over 2 radians. We know that this opposite side to it is called the hypotenuse, and we can give names to these different sides here, A, B, C. We could do the same thing with the angles. But one of the things that you absolutely can do, and anyone can do this, you could do it, I could do it, an alien on another planet could do it, is we can sit down and we can measure these lengths here, for instance. Oh, side A there, let me grab my ruler, let me use some measuring tool on a computer, let me estimate using my hand. It is 3 inches long, 10 centimeters long, one length of my hand along. An alien might be looking at it and use some weird alien unit like Zorbas or whatever, I don't know. B, the same thing, that's just a length. You can physically see that and you can physically measure it. Do you get what I'm getting at? The angles, same thing. You can take your protractor and figure out how many degrees are enclosed by this angle, how many radians, how many alien units of angle measurement are trapped within that little space there. These are things that we can objectively, physically measure no matter what unit system we're using. I say all of that to establish that that is not something that sine, cosine, and tangent are. When we say the sine of an angle, we're not describing anything that is physically really observable on this angle. And that's because of a very unique thing. That's because it necessarily has to be part of a right triangle, not just a single angle. And this is where the relationship between sine, cosine, and tangent and the right triangle comes into play. This is important to note. Yes, when we say the sine of theta, for instance, sine theta. Theta is, let's draw it on this triangle here, theta. Theta is an angle, but theta also necessarily must be part of a right triangle. It doesn't matter which angle it is. It shouldn't be the right triangle. The right angle. I'll just say that. It doesn't matter which of the two other remaining angles it is. It just has to be one of them, right? It can't just be some random angle. It is necessarily part of a right triangle. But theta is still just an angle. We're taking the angle on its own, not a right triangle when we're saying sine. We're not saying sine of a right triangle. It's not like measuring the area of a right triangle where it's one single measurement. No, because we can take the sine of theta, we can take the sine of this angle over here, we can take the cosine of theta, we can take the cosine of this. Do you see what I'm getting at? There's a lot of different things we can do. But really when we say sine of theta or cosine of theta or tangent of theta, what we're doing is taking the angle, it's a function, right? So we're taking that angle and we're turning it into a description of the right triangle. We're taking the angle and using it to describe a right triangle. Let me break that down. So really, one of the ways we can, instead of describing an angle, we could describe lengths, because lengths and angles necessarily must be related on a right triangle. As you shrink or grow, for instance, this angle theta, you would expect the lengths here to start shifting as well. If you started to shrink theta back and back and back, that length A here is also going to start extending out as that angle gets smaller and smaller and smaller. So to describe these things in terms of lengths, I'll write these out here and then repeat a very well-known pneumatic device for these. The sine of theta can be described as, using our diagram here, that's going to be length B over length C, where B is this leg and C is the hypotenuse. Cosine is going to be A over C, and tangent of theta is going to be B over A. And this is, of course, where I'm going to introduce the old favorite Sohcahtoa, which is a fun thing to say, kind of weird thing to spell out. But if you break it down right, S sine is the ratio of the opposite leg to the angle you're looking at, over the hypotenuse, B over C. Cosine is the ratio of the adjacent leg to the hypotenuse, A over C. And tangent is the ratio of the opposite leg to the adjacent leg. So Sohcahtoa. That's a very useful pneumatic device. It helps keep these things straight, definitely. And an interesting thing about this is, like I said, this really does help kind of bridge the gap between an angle and a right triangle, because inherently for any angle you draw, you can always make a right triangle out of it, right? If you have an angle, call this one phi, right? Just draw, even in this little drawing here, right? Just draw a line down like that, bam. All of a sudden you've got a 90-degree angle. And that is a right triangle right there. And as long as phi is that defined angle, whatever this is, say 60 degrees, there will always be a corresponding angle over here. Let's do the math. 180 minus 90 minus 60. Remember, the sum of all the angles in a triangle has to be 180 degrees. So this will be 30 degrees. And then the ratios of these lengths will always be the same. And remember, the ratio is the important part. Because, of course, this could be, on the scale of miles, or it could be on the scale of inches. We don't know how big this thing is exactly, but the point is it's always going to maintain that same shape, even if the size varies. So sine, cosine, and tangent are really just clever ways of taking an angle and describing something that can physically exist around that angle. It's taking an angle and saying if a right triangle exists around that, and sometimes the most basic interpretation of that is just a right triangle geometrically sitting there, on a flat piece of paper, or a right triangle, if you're approximating some wedge design on a rock or something like this. I go back to rocks because geology guy, right? But, right triangles are all around us geometrically in nature. But of course, sine, cosine, and tangent, trigonometry, have applications far extending beyond what is immediately observable in geometric terms, right? This goes into signal processing, alternating circuits, these kinds of things, a little bit beyond the scope of this video, but for those of you who have that kind of background, really that is what you're doing, right? You're making, what you're saying here is, yeah, this exists. If we were to make a right triangle relationship between an angle and some physical quantities, whether they're actual lengths or something else, this is what it must be. So that's sine, cosine, and tangent there. As a final note, I'll say sine and cosine can be easy to remember because here's a maybe 5-cent word for the day. Sine and cosine, not tangent. Sine and cosine, not tangent, are normalized. And that means they range between -1 to 1. And of course, because the legs of the right triangle are always shorter than the hypotenuse, you know that sine and cosine must never end up somehow being greater than 1 or less than -1, right? Anyways, I think that'll about do it here. I intended for that to be pretty brief. Maybe I started rambling a little bit about some of that. Hopefully that was a kind of clever introduction to sine, cosine, and tangent. Maybe not. If it wasn't, then I'll be back to kind of improve my lecture with subsequent videos. So that'll do it for now. See you in the next one.